Alright, I believe it's starting now. Let's see. Although I don't know why this screen capture isn't working anymore. Okay, I'm gonna delete this screen capture and then add a new one. Mac OS screen capture. Okay, hide OBS. Display capture. Built-in Retina display. Alright, minimize this. Bring to front. Move to top. Alright. Okay, I'd say that's good enough. Alright, now I kind of want to finish this notebook on portfolio theory. Then I think after this, I'm gonna just do some studying and work through our notebooks, kind of get an understanding of what's going on there. Okay, so let's see. Now I have no internet. Data, science, homework solutions. Homework assignments, lecture notes. And then we have the macro policy, portfolio theory. Okay, portfolio theory. Key text. I think it's transpose. MM. Okay. Oh, matrix multiplication. Alright. Yeah. So RF plus RF minus. So RF is equal to a scalar. We have RF plus R minus RF transpose that's X. So let R denote my one vector. Okay. So R is equal to vector, right? We have X transpose at pi vector transpose at X. The matrix. 1 by 1. Okay. So we have risk returns minus risk-free rates times transpose. So it'll be n returns n by 1 at, this will be an m by 1 vector, where n is a number of, I guess you call assets in our portfolio, risky assets. So yeah, n is a number of risky assets. So this one is X transpose pi. So that's also a X transpose should be n by 1. So this is also n by, that'll be 1 by n. This will be n by 1. Okay. Then X transpose sigma. So it'll be 1 by n, 1 by n times n by 1 I think that's just a scalar. Wait, I think these are all scalars actually, right? Random variable. So this is, yeah, this actually gives you some number. It's random variable 1 by 1, 1 by 1. This is also a is non-negative because a covariance matrix itself is you can have negative covariances, right? That makes sense. X transpose be n 1 by n times n by n 1 by n times 1 by times n by 1. Can a covariance matrix have negative values? Is that right? Covariance. So maybe if assets are correlated with each other. all of them negatively correlate with each other. Can that happen? So negative, everything is negatively correlated with each other, and the variance is 0. Okay, so I feel like it's 0. It's 0. I could say the calculation is 0 when covariance matrix, when the sets are not each other and have 0 variance. When the returns, the assets are independent, 0 variance. Okay. Can you change the number of assets? Scalar multiplication. -1 is delta t denotes a very short period of time. We can accurately approximate returns over an interval of length delta t, the Taylor series approximation. Care must be taken due to the way Brownian motion works. Let the expected return be Rf plus pi times delta t, and the volatility be sigma. The actual return is R is equal to Rf f plus pi minus sigma squared delta t squared sigma times delta b determines press sigma times change around ratio for this exponential. Yeah, that one is hard. The number of acids in the specific. Two climbing guys. The serum is from college with common boiling condition. Change the sign rather. Okay, so portfolio theory, we have pseudo-inverse singular value decomposition, Cholesky, relations. Okay, so portfolio theory. Oops. Value of money, real estate, linear regression exercises. Okay. Python. Anaconda, alright. So this is using the pseudo-inverse. pseudo inverse this one is using singular value decomposition. Cholesky. Cholesky. Okay. All right. So change the number of assets in the specification for the covariance matrix. So n pseudo inverse G pi is equal to RG intervals. Size is equal to n. Okay. Okay, I'll just delete these for now. So now it's just defining things. Okay, so this is where we can run our first. Okay, and then also we can add this. Oh yeah, what did he have here? Constraint optimization. I think it was right. And then the pseudo inverse. Okay. All right. So pi sigma is equal to Cholesky, right, print. Okay, yeah, I'm gonna delete those. Right. Then also I kind of don't want this print statement here. All right. So it is pretty close to 0. Okay, so what I really want to see is what is this sigma thing? So print sigma. Is this our covariance matrix? I think so. It's 0.2. So we can try to make the covariance matrix poorly conditioned by making some of the covariances to be negative. Okay, so I think I'll have negative sigma times. So these are the negative weights. Huh, okay. So I could say, yeah, this will crash. This makes it so that the matrix is no longer PS positive semi-definite. confused on whether or not if you take x transpose x, will all the things be positive here? I kind of want to write that down. Okay, wait, so if you have 1, 0, 1, -1, -1, -1, so let's transpose the rows. Rows, or the columns become the rows. Okay. So this is equal to 1. Two, so it'll be 2 times 2 times 1 is 3. 2 times -1 is -2. Plus 1. So, okay, so you can still have negative. So, right, x transpose x doesn't necessarily guarantee that everything in the resulting matrix is going to be this. And yeah, I don't think so. Yeah. Cholesky. Positive definites. So what does positive definite matrix mean? Positive definites matrix. Oops. What is a singular matrix? I see, yeah, so not necessarily. It's no longer positive definite. semi-definite, meaning X transpose sigma sum X. Is negative. Okay. In the principal, okay, wait, principal formula is this a bracket and series and problem change thing? Okay, so is the pseudo inverse more accurate than pseudo inverse more accurate compared to singular value decomposition? Okay. So I think he has the code here. We're taking the pseudo inverse. I think that would look, okay, so that would look something like this. And let's see. If these are the same. Minus SVD. Okay, pseudo inverse. Cholesky pi minus sigma at X. So it seems like they're pretty similar, actually. Simply changing the covariance matrix to be negative. Okay, what did I change it to exactly? To negative print sigma -2, okay. Negative 0.2 doesn't seem to actually make the pseudo inverse that much less accurate. See the first print statement. Okay. Okay. Let's time all of these algorithms. See which one is the fastest. Alright. And then we'll bring this back to, what was it before? I think it was 2.2 squared. Oh, right. So x transpose x, if x is a vector, is the same thing as squaring everything. But x transpose x when x is a matrix is not the same thing as squaring everything, because you have different columns that could be. Okay. All right, let's crank this up to 100. Yeah. Okay. We have the P inverse. We could do Cholesky. And then we could also do, I don't think we have an SVD yet. Okay, so we could import time. Okay, so we can time that start. Time starts Pn. And P inverse start X start Chol and Cholesky starts pi SVD and SVD. Oh, okay. Wait. And then we print. Call this P inverse time. And then we could end P inverse minus start P inverse. Start Cholesky time, start SVD, so end Cholesky, start Cholesky, and then end SVD, start SVD. Okay, so it does seem like Cholesky does perform a little bit better. Ooh, with 10,000 assets, yeah, it seems like it's gonna. Maybe that's too much. Oh man, yeah, this is not good. I think I put too many. Oh shit, yeah. Okay. I made n too big. All right. Okay, that's right. Okay, then we import this. Oh yeah, Cholesky still takes the best. With 1,000 risky assets, Cholesky computed the optimal weights the fastest with a well-conditioned Graham matrix. Okay, so I think it's positive, definite, right? Okay. Huh. Because this is a number that represents the variance of the portfolio. Folio. Compute the vector. If you compute the vector, the row vector times the column vector, give us a number, square, column vector, column vector, column vector. Folio. Yeah, there's gotta be a better explanation to just why that is non-negative, even though. Ooh, okay. Okay, so apparently the matrix itself has to be positive semi-definite. In the notes, the matrix must be positive semi-definite. Yeah, you have three different assets with zero with all negative covariances. Or maybe they're in three different industries that are completely. So I might need to watch the video for that again. Snapto recordings. Files, recordings, review sessions.
Submit what you have now and then submit again.
Oops, that's not it. That's not it. December 8th. Oh, wait.
Okay, I just now pushed the record button, and what this says is much worse than the expected return, and that's because if you have a bunch of bad outcomes, you're getting half. So maybe you make the wrong mistake. Or excuse me, you make mistakes because you'll you'll put into your assumptions whatever biases the calculation towards buying a house. So it used to be very easy squared. Then it would represent, and it was the R/2 multiple ways, and it might change signs over the business cycle by a factor of 2, but the standard deviation is the square root of the variance. So the variance goes up by a factor of 4. So that creates a quadratic function of the portfolio weights. And you can then ask yourself, okay, how do I maximize that quadratic function and therefore calculate a portfolio that would be my optimal portfolio. So that's the preamble to it. And the way the notes work is I went through an example with 1 risky asset, then an example with 2 risky assets, then an example with an arbitrary number of risky assets. It could be 1, 2, 3, 4, 5, or 500. And if we work from the 500 backwards, if you have the expected return that's a function of 500 portfolio weights, and you've got the variance that's a function of the 500 portfolio weights, that variance is what we call a quadratic form. And essentially, it's got a covariance matrix in there. And what you should remember is that a covariance matrix has the variances along the diagonal. It's a symmetric matrix. It's positive semi-definite, which just means that the variance of anything, any portfolio, is going to be greater than or equal to 0. And to calculate the optimal portfolio that kind of maximizes the trade-off between mean and variance, what you would like to do is find the vector of portfolio weights that maximizes that mean minus variance objective function. And the if you
what are the unique properties of the covariance matrix? So the unique the covariance is a symmetric square matrix has the following unique properties. So for one, it is symmetric, it is positive semi-definite, symmetric, has negative, it is symmetric, it is positive square. Okay. Is a code definition of a covariance matrix is that this may not exist in the real world. It is a good illustration. of semi-definites. See. Oh no. Oh man, okay. This Taylor series expansion looks so crazy. I honestly have no idea what's going on here. Yeah, man. I wish maybe one day I'll come back to it and rewatch this live stream, but oh my god. So if delta t denotes a very short period of time, we can accurately approximate returns over an interval of length delta t with a Taylor series expansion. A Taylor series approximation. I don't even remember what Taylor series is from calculus. K must be taken due to the way Brownian motion works. So if you let the expected return be the e raised to the rf plus pi times delta t, and the volatility be sigma, the actual return is r. Okay, so it's the expected return minus sigma delta t, just for the convexity of sigma squared delta t, the term sigma squared. Okay, so is that geometric Brownian motion, or is that regular geometric Brownian motion? Mu plus sigma squared divided by. Okay, so I think this is the geometric Brownian motion. So we subtract squared, right? Times delta t. plus sigma times delta B, where the square. Okay, wait. I have to look up this one photo that I took from my professor. So I'm cute, damn. Yeah, my professor gave me an index card a while back. I'll try to find it, of explaining this geometry. Oh, let's go. Okay, so minus 1 it's a Brownian motion. So log of R. So that's Brownian motion. Okay. So I'm right in thinking that this is Brownian motion. Which I think this case this would be plus delta t. Right, because we need to add. Plus 1 minus alpha plus alpha times RF plus pi minus 1/2 sigma squared delta t plus sigma e raised to the expectation of the Brownian motion times delta t. Okay, I have to. This 1/2 sigma squared thing is still kind of confusing, so I'm going to look at the homework solutions. Okay. Similarly, Brownian motion. Exponentiate it. This is the expectation times sigma squared. So the expectation of a Brownian motion process then is just so it's the Brownian motion. So it's Brownian motion. Equals expectation. So that's return. Minus sigma squared. Just for the convexity. Times delta t plus sigma times delta b. Which actually defines the exponential function we have. E of y is equal to 1 plus y. So first, there's a term of order delta t because of Brownian motion definition of p of t. Pt squared is equal to implies expectation of the change in Brownian motion squared is equal to delta t. In terms of factors like delta b are small relative to the first order terms of order, delta t can be dropped. Therefore, the Taylor series approximation to returns is r is equal to r minus 1, which is equal to rf plus pi minus times delta t plus sigma times delta b plus 1/2 sigma squared. Right, so This one's pretty tough, but primitively minus 1/2 x squared. Primitively when working with the Brownian motion. But I understand that when working with Brownian motion, we need to adjust the mean of this is the expected return mean by negative 0.5 times by / 1/2 sigma squared due to Jensen's inequality. X times minus sigma squared plus sigma squared. So plus the Brownian motion. Okay. Zero. Canceling out because the expectation of delta B is equal to 0, which eliminates many of the variables when canceling, when taking the expectation of the Brownian motion. Verify that the implicit approximation to R times something minus. Okay. Yeah, I'm gonna be honest. I have no idea how to do this one, and I don't really want to spend that much time working on this one. This one I have no idea. Okay, maybe I can just code this up. So RF is equal to 12. Delta T is equal to, let's see, 1 divided by 12. 12, 1 divided by 12. Okay, so 12% annually. One month time horizon. Okay. Then we do np dot exponentiates. Import numpy as np. Okay. Let me import scipy. Import scipy. Okay. So we have RF times delta T minus RF times delta T. Alright, let's see. Yeah, okay, this is pretty close. Minus 1. Error is really small. Okay, let's go. Got the portfolio theory exercises done. I am going to submit this, go brush my teeth, and then probably come back, go through some flashcards, and then head to bed. So let's go to assignments, portfolio theory, drag and upload here. So investments, and then we have BUFN, lectures, portfolio theory exercises, submit assignments. Okay, nice. Alright, let me just make sure this is the right one. Okay, this is definitely not the right one. New attempt. Okay, nice. Nice. Alright, I'll be back. Yeah, that was. What? You think it's that?
Yes.
Okay. Yo, shout out Allie real quick. Allie, if you're watching, no, there's no one watching, but thank you for commenting on all of my streams. I love you a lot. Alright, now let's get some of these flashcards done. Also, fuck this guy named Teddy. He sucks. JK. He's the roomie. What are some costs associated with property ownership? So some of the costs that are associated with property ownership could include your transaction costs, your insurance costs, taxes, your reinvestment costs, and also your routine maintenance. Trading strategy and homework 2, question 2. You roll over bonds. Instead of riding yield curve, you get a higher return. It's a basic idea. Why are we in peculiar times with the real estate market? So interest rates are high compared to the period of 10, 15 years since the housing crisis, in which interest rates were pretty much at near zero. And then now also interest rates are at 5%. Inflation is slowing down, and the Federal Reserve, in the summary of economic projections, estimates that there could be rate cuts coming soon in the future, which is making a lot of investors, and especially equity markets, very bullish. I wonder what the summary of economic projections are. Okay. Summary of economic projections. To employment rates. Seeing rate cuts, okay. What's the next one? It's not looking at any more rate hikes, that's for sure. Okay. So I guess with the summary of economic projections, a lot of the Federal Reserve members are considering cutting rates in 2024 and most likely won't be actually raising interest rates. So there could be also a risk of I think that consumer savings right now is a lot less than what it had previously had a year or two ago, and it'll be interesting to see what housing market is going to look like in the next few years. Singular value decomposition is just a way of decomposing a matrix into 3 other different matrices. So I believe one is U and V. U and V are both n by m orthonormal matrices. So we take U transpose U transpose D, which is a matrix of singular values. Singular values by a matrix. M by n orthonormal matrices. M by n. M by m. Yeah, wait, that doesn't make sense. M by n. This doesn't make any sense because you can't multiply an m by n matrix with a m by m matrix. So let me see what I did wrong here. Oh, these are n by m. Orthonormal matrices. How is an equity security like a fixed income perpetuity? It's like a fixed income perpetuity in the sense that you get these cash flows until pretty much the end of time. But they are not like a fixed income perpetuity in the sense that if a company does get bought out, then the actual, like you can say cash flows or dividends get paid back to the equity holders. What is each realization of a Brownian motion process? It's just a sample path. And what does it mean when modeling asset prices? When modeling asset prices, this is just a possible fluctuation in returns for a company. What is a normal equation for the first order condition of the sum of squared errors objective function? So the sum of squared errors objective function is just the y minus x times b, where x is a matrix, b is a vector, y is a vector of predictions, xb is a vector of predictions, and y is the actual, I guess you could say, value, and then we just multiply that twice. We could say we transpose the first one, okay. Oh, and then the first order condition, I think we just take the derivative. This is x transpose x times b, which is x transpose y. Transpose y. Okay. What does an increment represent in the Brownian motion process? What does it represent when modeling asset prices? In the Brownian motion process, an increment just represents a change in the actual price and a change in value over time. And it just represents when modeling asset prices, it's just the change in value, change in price over time. Okay. How does a discount factor using simple interest value $1 compare to discount factors using compounding or discount rate conventions? So I think simple interest would value $1. It will value it differently, and I think it would value $1 more compared to using a discount factor that has compounding or maybe a discount rate. Discount rate and simple interest might be the same because they both apply some type of linear discount to, or they both introduce the idea of linearity. Given the following, so 3 dates. So this function, this expression just represents that. The expectation, okay, so the RT0 M1 times M1. Okay, so this is just saying, this is kind of disproving the expectations hypothesis in the sense that your implied forward rates, or I guess you could say holding a bond until maturity from T0 to T2 does not give you the same return as buying a bond at T0 holding until M1 and then buying another bond at T1 and holding until M2. Expectations hypothesis. Oh yeah, this is pretty tough. The expectations hypothesis of the term structure. Just writes, okay. So expectations hypothesis just says that the forward spot rate, so the actual interest rate in the future, is exactly equal to the implied forward rate. The condition number of the matrix is the ratio of the highest versus the lowest singular value, and I think it's the lowest divided by the highest. The condition number of identity matrix is just 1. So yeah, this is wrong. It should be smallest singular value, largest singular value. Okay, close. Future spot rate is just the actual interest rate in the future at some time. Same. Then there were the clause investments in long term same returns, rolling over to another short-term security. Another way of saying this is that the future spot rate, actual rate in the future, is usually different than the implied interest rate by the future by the market today. Okay. If interest rates are positive, how can we describe the function df t0 and discount factor, given the date today, t0 and maturity in the future? So the discount factor is the present value of $1 to be received in the future at maturity M. The present value of $1 today, T0. Oh, describe the monotonically decreasing function is maturity. So if interest rates and discount factors represent the same thing, why do we need both? Discount factor is in dollar terms, interest rates, percents. Okay, prices are most useful to model financial and economic concepts. Interest rates help with coding and modeling. Okay. How do you know if a matrix is invertible? If the determinant, I think, is 0, if it's square, and the columns are linearly independent. Okay. What experiment did Pete run with calculators? So with the calculators, he made an experiment where he tried all of these buy or rent calculators, and all of them ended up telling Pete to buy a house, even though in some cases it might have been smarter to rent. Okay, what are some possible reasons why housing prices might be seasonal? Could be due to the weather, could be due to housing leases or apartment leases expiring in the summer most of the time, could be due to families moving during the summer because it lines up with school seasons. Okay. Practice, what are ways to think about duration according to Pete? So I think he thinks there are I think this might be going back to a theoretical version or an approximate version using the yield to maturity, or a theoretical version using the actual yield structure or term structure, yield curve. But duration we can think of as the present value weighted average time until maturity, and maybe according to Pete, it's how sensitive your investment is to interest rates. Percent yield to maturity. Okay, kind of got that right. Grand matrix is the resultant matrix from the X transpose X. Matrix product of the transpose itself. So, applied forward rates is the forward rates or the future interest rate that is implied by term structure, so that if you held the bond from today until, let's say, 5 years from now, you would have the exact same return as if you hold a bond for, let's say, 2 years, and then sell it, or it matures, and then reinvesting again in 2 years in a 3-year bond. What is the normal equation for the first order condition of the sum of squared errors objective function? So I think this is X transpose X is equal to X transpose Y. Oh, X transpose B. Okay. Oh. What is the Brownian motion sample path? It's just the realization, or it's just used to kind of describe the possible path of an asset price. It's a sample path. It's a function of continuous variable time. Okay, kind of got that wrong, but I'm gonna just skip this for now. When is compounding really take into effect way later on in the future? Usually, right, I guess in the beginning years, if compounding, continuous compounding, discrete compounding, or simple interest usually give similar returns. Given a following x is equal to m by m matrix representing n observations on m variables, y is equal to a vector representing observations of the variables to be explained, and epsilon is equal to a vector of identically and independently distributed errors, b is equal to a vector of unknown regression coefficients. How can I write an equation that captures the essence of linear regression? So I think we could say that the vector representing observations of the variable to be explained is equal to the matrix vector product of A and B, and we add some error E. What is the duration of a coupon on less than its maturity? So the duration of a coupon bond is less than its maturity because cash flows are weighted more in the beginning half of the present value of the cash flows received at some date is weighted heavier in the beginning of an investment. And so because all of the weights eventually sum up to 1, all of the most of the weights will be higher in the first half compared to the second half of the actual time until maturity. Yeah, that one's pretty bad. A matrix is invertible if it is square, and also its columns are linearly independent. Duration is the present value weighted average time until maturity. So mathematically, we can think of the weights as the present value of the cash flow we receive at some period. So whether it's 0.51 to 2.5, where the 1 and 2 can be represented as delta t, which can be thought of as the number of years in which are starting from today in which a coupon payment is paid out. So we calculate the present value of that actual coupon payment, and then we divide that by the present value of our entire investment. And then we multiply each of these weights. We take the inner product of these weights and also the time delta t in which we receive each of those cash flows. So I guess you could think about it as a measure of interest rate sensitivity. So a shorter duration will have lower interest rate sensitivity compared to investments with higher duration. And also you can think of maybe duration as the time until maturity, the time that you would receive the entire present value of your the time you would theoretically receive the value of your current present value. Okay. The initial number of a matrix is the ratio of the lowest singular value to the with the highest singular value. The condition number for a matrix is just one. So you call it a singular matrix. Okay. This one's hard. So if integers are positive, then that means the function of discount factors, df t0 m, given the date today t0 and maturity in the future m, we can describe it as a monotonically decreasing function in the sense that the present value of $1 is going to decrease as the maturity increases. Just a result of the matrix matrix product. So m transpose x, m x transpose x. X transpose x to the Gram matrix times b is equal to x transpose y. Okay. Veritable if it's square and also has its columns are linearly independent. So, given the following x is equal to m by m matrix representing n observations on n variables, okay, I think I'm good for now. We just passed 1. I'm going to stop the stream, but exam is tomorrow. I think, hopefully I'll be ready. If not, oh well. But yeah, I'm excited. I'm gonna go watch some YouTube probably, maybe some Instagram reels, and then wake up at 8:30, 9. It's currently 1, so maybe get 7 hours of sleep, and then get to it. Alright, bye.